program is an ETV presentation of DIFC Television. Produced in cooperation with the Department of Engineering Mechanics. This is Engineering 402, Professional Engineering Development. And in today's lesson, we'll discuss the mechanics of materials. And now, here's your instructor, Captain John Sullivan.
Hello. Welcome to our third and last episode in our three-part series involving the mechanics of materials. Today we'll have two lesson objectives we'd like to cover. First of all, we're going to review some of the material we've had before and cover a technique called combined loading. You might find some of that the review or a repeat of what we talked about before. Our second lesson objective will be to take the combined loading and discuss Moore's circle. Moore's circle is a graphical technique used to find the total state of stress at some point in a loaded member. With that as an introduction, let's get started today. As I said before, some of the material we'll cover today will be a review of what we've seen before. Combined loading involves the combination of three basic types of loads: axial loads, torsional loads, and bending loads, all of which we've covered today. But it'll be worthwhile to look at each one separately again, just briefly. Recall, axial loads refers to the fact that if we're given a member, it might be loaded in a direction parallel with its lengthwise axis, as we see here in this picture. We discussed before where we cut this member perpendicular to the direction of the load to expose a cross-sectional area we called A. The stress involved, or that the cross-sectional area A would feel, is called a normal stress, and it's given a Greek symbol sigma. It's equal to P, the applied load, over the cross-sectional area A. We've seen this before, but it's important to realize two things. First of all, that the normal stress due to this type of load is constant throughout the length of the loaded member. Second of all, that stress is evenly distributed over the cross-sectional area. Let's compare that now with the next type of loading, torsion. Torsion involves some engineering material, and it's loaded in a twisting manner, represented by a torsional load here, T. Let's cut this member at some cross-sectional area here with the dotted line and look at its cross-sectional area. I've represented that simply by stepping into the blackboard perhaps and looking straight down the axis of the shaft that we've got loaded in tension. We see here the applied load T, or the internal torque, and a small portion of the area that I've labeled here a distance rho from the center of the shaft. We recall that the shear stress that that small portion of area would experience is equal to the internal applied torque, T, times the radial distance we called rho, and this was a cross-sectional property. J was called the polar moment of inertia. Let's recall two things now. Again, the way the torsional load, or the shear stress due to torsion, is distributed through the length is constant, meaning that throughout the length of our loaded shaft here, the shear stress is distributed in the same manner throughout its length. Compare that, however, with the way the shear stress is distributed over the cross-section. By virtue of the fact that the shear stress is a function of the radial distance rho, it increases as we approach the outside surface of the torsionally loaded shaft, and it's also zero through the center line of the shaft. These two facts will be important to remember when we go on to combined loading. But before that, let's look at probably the most complicated form of loading, that due to bending. As you remember, bending causes both kinds of stress, normal and shear. Let's look at each one separately. Under a bending load here, I've given ourselves an example. Here's a simply supported beam under some centrally applied load P. Let's cut this member here on the dotted line to expose the normal surface. And let's look first of all at normal stress. I've suggested here that we've cut our beam. Here's our knife edge to expose the normal surface. The x-axis runs through the axis of the beam here, and it's also represented as the neutral surface, recall. Y is measured from the neutral surface, usually positive upward, but some textbooks vary. Some measure positive Y downward. Don't worry about that. Recall that the normal stress due to bending is a function of several properties. First of all, M. M is the internal bending moment. We would usually find that from the bending moment diagram, you recall. Y, as I said before, is a distance measured from the neutral surface. Some texts will use Y positive upwards, some positive down, and I is a cross-sectional property called the area moment of inertia. Notice a couple facts about the way this stress is distributed across the cross-section. By virtue of the fact that Y appears in the formula, the normal stress increases from 0 at the neutral surface and increases to a maximum at the very outside surface, both at the top and the bottom of the beam. Now let's go back up to our first picture here on the top. This picture, I can imagine what the bending moment diagram would look like for this, strictly due to practice. I know that the beam would experience a positive bending moment throughout its length. I have used that rationale to explain my picture down below here. A positive bending moment would place the top fibers of our beam in compression, and I've represented by that an arrow, perhaps suggesting it's pressing against the exposed area. Compare that with the exposed area below the neutral surface. It would be in tension or being stretched due to the positive bending moment. I've suggested that by an arrow perhaps pulling on the lower surface. We'll have to remember not only the formula for normal stress due to bending, but also the manner in which that stress is distributed across the cross-section before we go to combined loading. The last thing we need to cover now, shear stress. Shear stress is a little difficult to represent in the picture here, but I've done the best I can. Again, I've cut our beam here, representing the knife edge with some length of beam, and here's our saw cut passing through the beam, exposing a cross-sectional area. Again, as before, the x-axis runs through the center of the beam, through the neutral surface, and Y is measured in the same manner, away from the neutral surface. Shear stress, you recall, involves the shear load V times a cross-sectional property we called Q, divided by the same cross-sectional property we've seen before, the area moment of inertia, and the thickness of the beam at the point where we want to find the shear stress. Note again now that the shear stress is distributed in a parabolic pattern across the exposed area here. It reaches a peak at the neutral surface and tapers off to 0, both at the top, at the bottom, and the top fiber of our beam. Okay. Now before we go to our first example, remember we're going to have to take into account both factors. Due to bending, normal and shear stress will vary, both with respect to the distance along the beam. For that, we'll look at a shear and moment diagram. And by virtue of their formulas, they also vary across the cross-section. Let's look at our first example. Imagine a beam here of length L extending beyond or extending out of a wall. It's got 3 different types of loading on its free end. A torsional load I've labeled T, an axial load P, and some bending load here I've called W. Also over here, I've represented the cross-section of the beam. Notice it's circular. Okay. I've also listed down here values for the various loads. The weight, or perhaps suggested by W, is 200 pounds, an axial load and a torsional load, and the length of the beam. The first task would be to draw a free body diagram. I had to squeeze it into the blackboard here just a little bit, but here's my applied loads. On this end would be all the appropriate loads that a fixed support is capable of providing. By summing forces and summing moments and so forth, I can find that the appropriate vertical load would be equal to the weight W. The torsional applied load would be equal but opposite to the applied torque T. The axial load would be equal and opposite to the applied load P. And lastly, the wall also could support a bending moment. By summing moments about some point, I'd find that it's equivalent to W times L. With that as a preliminary, we're ready to draw a shear and moment diagram. We should be able to produce a shear diagram very quickly. Remember, plot on the vertical axis a representation for the shear force V. A horizontal axis should represent the length of the beam, call it an axis X, and we simply plot the external loads as though they were the shear loads. So we go upwards to a value of 200, the value of the weight W. There is no change in the distributed load throughout the length, so we close with a last vertical load downwards, also equal to 200. We've closed at 0, so we're assured that we've done this correctly. Let's go on now to the bending moment diagram. The bending moment diagram is plotted with a vertical axis representing the internal bending moment. The horizontal axis extends through the length of the beam, represented by an x-axis. The first external bending moment is up above here on my free body diagram. It's equal to WL. I'll have to plot that as my first external bending moment. It's negative. WL turns out to be 24,000 inch-pounds. From this point, I know that the change in the bending moment is equal to the area under the shear diagram. Let's go up above again. The area under the shear diagram would be 200 times the entire length of the beam, 120 inches. My change in bending moment diagram then is a positive 24,000 pound-inches. Again, I've closed at 0. This must be an accurate picture of the bending moment internal to the beam. Now, before we go on, I really haven't posed a question in this example, only described it. Suppose we wish to find the state of stress at some point located inside this beam. For example, we might like to find the state of stress along the top surface or along the bottom surface. Our success at finding those surfaces, those stresses, is predicated on our knowledge on how each of these loads distributes its stress throughout the length of the beam. Suppose we state the problem a little differently. I'd like to find the maximum shear and the maximum normal stress throughout the beam. We haven't decided a specific point. It would be up to you to find it. Okay. Let's review a little bit then. The axial load P will provide a normal stress evenly distributed throughout the length and across the cross-section of the beam. The torsional load will provide a stress that's evenly distributed through the length of the beam, but will vary depending on the location in the cross-section. The bending moment caused by the weight W will cause both shear and normal stresses. They will vary throughout the length and the cross-section both. With a little thought in mind, we might realize that the maximum normal stress may occur up here on the top corner of the beam. Okay. This is due to two facts. We know that the bending load will provide a normal stress that will reach a maximum at the top and the bottom surface, and that stress will also vary with the bending moment diagram. You recall our bending moment diagram down below. The maximum bending moment occurs clear back at the wall. The maximum shear stress, let's compare it next. You recall that the shear stress due to torsion will vary throughout the cross-section. The shear stress due to the bending load, W, will vary throughout the length and the cross-section. We should be able to tell where the shear stress would be maximum by looking at the shear diagram. The shear force is constant throughout the length, but I know that the shear stress will be a maximum through the neutral surface. So we suspect up above the maximum shear stress will occur at any length through the neutral surface of our beam up above. Let's use this knowledge and go ahead and continue with our example. We're told to find the maximum normal and the maximum shear stress throughout this beam. Let's take care of the normal first. Axial load, that's the easiest to take care of. I know that if I cut the beam and expose a cross-sectional area, the normal stress due to the axial load is simply P over A, or the axial load 1,000 pounds divided by the area, 12.5 square inches. Turns out to be 80 psi, and I've labeled it specifically in tension. The axial load pulling on the beam would provide some tension in the material that I've cut. Let's take care of bending next. I've suggested we've cut our beam here very close to the wall, so you can tell I've only cut the very short portion of the beam. Let's call it virtually zero for the purposes of our example here. The bending moment applied here would be perhaps negative. I see I have my arrow drawn in the wrong position. It should represent a negative bending moment, providing a compressive load on the bottom and a tension on the top. I know the value of that normal stress is equal to the bending moment M times the distance Y divided by the cross-sectional property I. Let's put in the numbers here. 24,000 was the largest possible bending moment. It occurred at the wall. The distance Y is 2 inches from the surface, from the neutral surface to the very topmost part of the beam. I, we found, was 12.5 inches to the fourth. My example here, simply by coincidence, has the same number for I as cross-sectional area, 12.5. But I'll distinguish this by carrying its units, inches to the fourth. As you go through problems on the exam, I'd suggest you use all of the units appropriate. Pound inches here, inches here. That way you'd have a good way to check to see that you come up with the right number by virtue of the fact you'd come up with the right units in the end. Pounds per square inch. Here we have 3,840 pounds per square inch, and I've labeled it specifically. It's in tension, and it's located at the top of the beam at the wall. Now let's add these. Since they are both in tension, we'll simply arithmetically add both of the stresses. The maximum normal stress due to bending first, 3,840. Next, due to the axial load, is 80 pounds per square inch. My maximum normal load then, or stress, turns out to be 3,920 pounds per square inch. And specifically, I've labeled it as tension at the top surface of our beam, and it occurs right as the beam comes out of the wall. Okay. The location of these points is important to specify. Okay. Next, let's go to shear. Let's take the shear stresses first due to torsion. I've represented here a cross-section of our circular beam. The internal torque T is applied, and I've suggested here on a graph that the shear stress is distributed through the cross-section. It would be 0 at the center. As we move out towards the outside surface, the shear stress would increase by virtue of the fact that rho, or the distance from the center, appears in our formula. The maximum shear stress then is at the outside surface. We found that it was equal to the internal applied torque T. This time I've substituted R for rho since we're dealing strictly with the outside surface. J is a cross-sectional property. It turns out to be 25 square inches to the fourth. Okay. Putting in the appropriate numbers here, I find that due to torsion only, we have 32 pounds per square inch. And this would be at the outside surface of our shaft, or our beam. It'll help me to remember that this is distributed upwards on this portion of our beam. Okay. So let's go to bending next. Bending is a little bit difficult to depict its shear stress in a picture here. But here again, I have drawn the cross-section of our beam with the neutral surface passing through the centroid, as it should. And I know that the shear stress here is equal to the internal applied shear force V times a quantity we've called Q divided by I and the thickness of our beam at the point at which we want to find the stress. We are interested in the maximum shear stress. Due to bending, I know through my experience that it will occur at the neutral surface. So my first task would be to identify Q for that area. I've drawn a dotted line here, and I've labeled my A prime, as you recall, must be the area from a line through the neutral surface, or the point where I want to find the shear stress, to the outside edge. And I've labeled that A prime. A prime turns out to be just half the area, 6.25 inches squared. The distance from the neutral surface to the centroid of that area, I've labeled it Y bar prime. Many textbooks use the same symbol, others may vary. Y bar prime, I'd have to look it up in the back of a textbook under various properties. It's given to me as a formula, but in this case I find it's 0.85 inches. Okay. Q is the product of these two members, of these two quantities. It turns out to be 5.3 inches cubed is the appropriate units. Let's go back up to our problem now. The appropriate load here, internal shear load, is 200 pounds. Q, we just found it. I, we've seen it before. And notice here, be careful, there's a temptation to put in perhaps the radius of our beam at that point. This is the thickness of the beam at the point where we want to find the shear. Let's look back at our cross-section. Our cross-section is of 2-inch radius, but the total thickness throughout would be 4 inches. I find the maximum shear stress is 53 pounds per square inch. I've labeled it also, by a careful analysis and drawing a free body diagram, as an upward shear stress. Therefore, as I look up above, if I want to combine the two shear stresses due to bending and due to torsion, since both go in an upward direction at the same point in the beam, I would add these two fellows. Algebraically, 53 due to the bending load plus 32 pounds per square inch due to the torsional load. And I've labeled specifically where this occurs. It's at the neutral surface and on the right side of the beam. I use right side of the beam simply for the lack of a better term. As I look endwise on the shaft, this point up above here, I would call the right side, simply for my own notation. So we found our maximum shear and normal stress due to this combined loading. Let's use this knowledge now to find the total state of stress throughout any point in a beam, and there's a very popular graphical technique to do that called Moore's circle. So let's look at our example problem again. Moore's circle is a graphical way to find the state of stress at a point in a given beam. We're familiar with this beam here now from our previous example. What we'd like to do is find the state of stress and Moore's circle for a point B. Point B is at the neutral surface and on the right side of the beam. We know something about its stress already since we've used this as a previous example. We'll go through this and I'll illustrate how to draw a Moore's circle by means of an example. But critical to success in understanding this technique is understanding exactly where point B is in our beam. We're asked to find the state of stress there. As we go back over to our new blackboard here, let's identify the point B through various pictures we've drawn. Up above, the first one, point B is back here at the wall. It's at the neutral surface, so I've represented it here. Point B would be identified on the right side, so it would be identified as the spot I've identified here in this picture, or in the same cross-sectional area in our torsional picture on the right side. Now, critical also is to look at the condition of point B during bending. Okay. Our normal stress here, I've identified point B would be on the right side, be on the far right surface over here. Also important to note, the normal stress due to bending, point B would be right at the neutral surface. Point B would be right here at the apex, or where the normal stress due to bending would be equal to 0. All this is critical to understanding exactly the state of stress before we proceed to Moore's circle. So let's go over to our new board here. There are some preliminary remarks I could make before we go to Moore's circle. We see here I've repeated our picture. I haven't put any loads on it here, simply for simplicity, but I've identified where point B is. The neutral surface, back at the wall. The first task is to blow up a microscopic view of our point B, and I've done that over here. I've represented a small patch of material that's located at the wall, and I've identified it here. Our patch is the point B. On a vertical surface here that would be cut if I were to expose a cross-sectional area are the stresses that point B would experience. Recall, for example, the normal stress 80 psi would be in tension, and I've identified that perhaps as an x-axis since it's parallel to the x-axis in our beam. It's only 80 pounds per square inch. Remember, the stress due to bending at point B, or the normal stress due to bending, is equal to 0. The only stress that point B experiences is that due to the axial load. We found it previously to be 80 psi. In an upwards direction, I've represented the shear stress that point B would experience, 85 psi, both due to torsion and the bending load. Since point B must be in equilibrium, all the forces and moments must equate to 0. So if there is an 80 pounds per square inch stress pulling on this side of the beam, on this side of our stress block, there must be an equal and opposite stress, 80 pounds per square inch, on the opposite side. This will hold our block in equilibrium. There is no stress applied in the y direction, either up or down, so I haven't drawn any here. If there were, I would make them equal and opposite, just as I did with the 80 pounds per square inch. The 85 pounds per square inch due to shear is a little different case. This side proceeds upwards. In order to make the block stay in equilibrium, there must be an equal and opposite stress on the other side, downwards, 85 pounds per square inch. Well, now we see we have a net couple, or a moment applied to our block, due to the upward force here, the downward force here. We would have to negate that couple by applying an opposite couple. 85 pounds per square inch would be applied on the bottom surface to the left, 85 pounds per square inch applied to the right on the top. This is called a stress block, and it represents the equilibrium condition of our point B. Now we're ready to start drawing Moore's circle. Moore's circle will provide us a technique to find the state of stress at point B regardless of the direction of the surface that I am interested in. We do so in the following manner, and I'll embellish each of these steps as we go through our example. First of all, plot a normal and shear stress axis, just as you would an X and a Y axis. On that axis, plot the stresses on the stress block as though they were the coordinates of a point on our sigma tau axis. Those 2 points will provide a way to draw the diameter of the circle, and the last step would be complete that circle using the drawn diameter. Let's go through that step-by-step process over here with this example. It's difficult to represent a sequence of events here, but the first thing I did was draw a normal stress axis horizontal and a vertical stress that would be my vertical axis. It's called representing tau. This would be the center of my axis system. The next thing, I'm going to have to go back and forth between these 2 boards now here. I plot the stress on 2 perpendicular states on my stress block as points on my sigma tau axis. Let's go over here. This is a vertical face that I've cut. I recognize that there is an 80 pounds per square inch normal stress. There is also on that face a vertical shear stress equal to 85 pounds per square inch. Sign convention varies between textbooks, but the one I will use to continue through the example is I will consider this shear stress upward a negative value. So I'll plot the points 80 and minus 85 as a point on my sigma tau axis over here to the right. You see I've done so right here. The normal stress would be represented by 80 pounds per square inch. Down here a negative 85 representing the shear stress for the vertical face of my stress block. First point's done. Now let's look at the next point. Let's go back to our stress block here. A perpendicular face to the one I've just identified, the vertical, could be represented by this fellow here. I notice this face experiences no normal stress, or 0 sigma. It also experiences an 85 pounds per square inch shear. Consistent with my sign convention, I will call a stress here to the right on the top side positive. Again, sign conventions may vary with the particular textbook. I'll plot this point, 0, positive 85, on my sigma and tau axis system. You see I've done so here. Normal stress is 0, shear stress is positive 85. This identifies the point on my tau axis up here on the top. The next step I said was to use these 2 points to complete or draw the diameter of a circle. I've done so by connecting these 2 points with the diameter of the circle. Next step is to complete the circle, and I've done so by drawing a circle whose center, by the way, will always fall on the sigma axis. Now it's important to realize the way in which Moore's circle can be used. And here's the rationale. The points, or the coordinates of various points around this circle, represent the state of stress at various locations in our stress block. For example, we found that the vertical face over here experiences a stress of 80 pounds per square inch, normal stress, a shear stress 85 pounds per square inch due to shear. That, of course, is plotted as one of our points over here on our sigma tau axis, one of our first points we found. But various points around the perimeter of the circle also represent states of stress at other locations inside the stress block. There are 2 very important stresses that we would like to find. We note from the Moore's circle diagram that there are 2 normal stresses I've identified as sigma P1. P would stand for principal, thus these are principal stresses. This point and horizontally over here, the second principal stress. These points represent the state of stress, or a point on our stress block in which the shear stress is equal to 0. We can see that by our diagram. Both of these points represent 0 shear stress. As I said before, sigma P1 and sigma P2, the principal stresses, represent the locations of 0 shear stress. There are several geometrical techniques used, or algebraic techniques, to find the two normal stresses. I've chosen here to represent them as both in the same formula here. The first principal stress and the second. Both can be represented by summing the normal stress in the x direction and the normal stress in the y direction and dividing by 2, or finding the average stress. I would add or subtract that depending on whether I wanted the first or second principal stress to a term here that looks fairly complicated. The difference in the two normal stresses over 2 squared plus the shear stress acting on the stress block squared, and I would take the square root. Both of these would give me a representation of the two principal stresses. But perhaps if we look up closely here, I can identify a graphical way to find the two principal stresses. You see, I've labeled the first portion of our formula here C. This represents the center of Moore's circle. The second part of our formula I've labeled a capital R. This represents the radius of Moore's circle. Up in my picture up above, I also identified both of those. The center of Moore's circle, represented by this point, and the radius of Moore's circle, I've labeled it out here. And the radius, of course, would continue throughout. Okay. Where the location of the principal stresses are found is a little bit difficult to describe, but let's go through it as simply as I can. I notice that there is a relationship between the point I plotted first, representing the vertical face on my stress block, and the angle we'll call 2 alpha here, to the first principal stress. That means that if I rotate the stress block a distance alpha, not 2 alpha, I would find the location in the stress block where the first principal stress acts. I've done that down below here. I've drawn my original stress block as we would draw it the first time. I have omitted here the normal stress 80 pounds per square inch and the shear stress in the vertical direction for simplicity. But I have taken the face represented by my first point on Moore's circle, and I have rotated it in the same direction, but only half as much, alpha. This is the direction on which the first principal stress acts. If I go up to my picture up above again, what I have done is located the first principal stress. If I continue to travel around the perimeter of the circle, I have gone a radial distance of 180 degrees, or pi, to find the second principal stress. Let me travel half the radial distance on my stress block in the same direction to find the second principal stress. So let's go down below. From the first principal stress, I'll travel a radial distance equal to 90 degrees instead of 180 to find the location of the second principal stress. The two values for the principal stresses, I use the formula up above, and in the example we've been using before, we find that the principal stress through the neutral surface on the right side of our beam at the wall is 125 pounds per square inch in tension, represented by this direction. And in this direction, sigma, the second principal stress, would be minus 45 pounds per square inch. I've identified it as compression, since when we use our formula up above, we get a negative value for the principal stress. Supported by one further picture, I move further up above. The graphical representation shows our second principal stress in the negative portion of the normal stress. Okay. I think I've covered everything I'd like to cover here today in our last episode, and I hope I've done you some good virtually throughout the series on mechanics of materials. Now rest assured, the EIT exam will cover a great deal more material than I have covered here with this review. But I hope I have stimulated your memory a little bit so that you could perhaps remember things that maybe you thought you'd forgotten. So with that, I'll say goodbye, and I wish you the best of luck on the test. Thank you.
The following program is an ETV presentation of DIFC Television. Produced in cooperation with the Department of Electrical Engineering at the United States Air Force Academy. This is Engineering 402, Professional Engineering Development. And in today's lesson, we'll discuss the fundamentals of electrical engineering. And now, here's your instructor, Captain Frank Tiller.
Welcome to the Electrical Circuits block. This block will consist of 4 lessons. Today's lesson on electrical engineering fundamentals will lay the groundwork for the other 3. After we look at the fundamentals today, we'll then look at DC circuits in the second lesson, and then we'll spend 2 lessons on AC circuits. Today's lessons will start with some basic concepts in electrical engineering. The concept of charge and energy. And we'll call these our basic electrical variables. And from that, we're going to develop the basic circuit variables of voltage, current, and power. And after we've seen the relationships between these variables, we're going to define the input-output relationships for the 3 devices that we're most interested in this lesson, that are resistors, capacitors, and inductors. After we've looked at the input-output relationships, we're going to look at some of the circuit constraints in the form of Kirchhoff's voltage law and current law. And that will form the basic tool for analysis of both AC and DC circuits. And then after that, we're going to look at the different kinds of shapes that signals or waveforms can have. And then we'll conclude the lesson with a couple examples of some of these principles. So the first thing we want to look at to start the lesson is the concept of charge. Electric charge is a true electrical quantity that exists in nature as the charge of an electron, the smallest charge that you can find in nature, of 1.6 times 10 to the minus 19 coulombs, the unit that we measure charge in. We use the symbol Q, either a large Q for a constant charge or a small q for some time-varying q. And we abbreviate the coulomb with the letter C. Now, charge is both positive and negative, and we'll need to keep track of that fact in our circuit analysis problems. In electrical engineering, we universally deal with positive charge, the way that positive charge will move in the circuit. And this is going to place certain restrictions on our other quantities that we'll be looking at. Now, the fundamental principle that it then allows us to do both AC and DC circuit analysis is that of the conservation of charge. The fact that charge can neither be created nor destroyed in a circuit. And from there we're able to come up with Kirchhoff's voltage law and current law. The second basic electrical variable we need to look at is energy. And a charge can have energy associated with it. And energy is the potential to do work, and therefore has the same units as work, and can be expressed as a force times a distance. And that would be a Newton meter, which in electrical engineering we'll term a joule, the unit of work and energy. And the joule is abbreviated with the unit symbol J. We'll be using a W to represent energy. The other fundamental unit we need to work with is the unit of time, of course. Given these three quantities, current and voltage and power can then be defined. This table summarizes all the fundamental quantities we have to work with. We have mass, where we use the symbol M, and it's measured in kilograms. We have length, the symbol L, and it's measured in meters. Now the next three are critical for our work in circuit analysis. Time, of course, is measured in seconds with the symbol T, and energy with the symbol W will be measured in joules. The other quantity we looked at is charge, with the symbol Q, and measured in coulombs. Now, when we use the symbol small q or W, any small symbol will refer to the fact that that quantity can be time varying, whereas a large symbol refers to the fact that the quantity is restricted to some constant value. So using these three fundamental ideas, we can now develop things that are more easy to work with in electrical circuits. And the first quantity we'll define is electric current. Current is simply a measure of the rate of flow of charge within a circuit. We'll use the symbol I, and we'll measure current in amperes. Current is defined by this relationship as the time rate of change of charge, or a flow, if you will, of charge within the circuit. You can see that an ampere is equivalent to coulombs per second, based on this fundamental definition. Now, because we have positive and negative charges, we have an associated direction for currents. The direction that we're interested in is the direction that positive charges would move within the circuit. So we must keep this in mind in our analysis. The next quantity we're going to define is that of voltage. And again, it can be related to our fundamental quantities of energy and charge. As you can see from the definition, it's a change in energy per some small packet of charge as it goes from point A to point B within the circuit. And we measure voltage in units of volts. And it's equivalent, you see, to joules per coulomb. And we'll be using the symbol V for voltage. Now also, just like current, which has a direction, voltage has a polarity, which must agree with the current direction. We have one side which is at a higher potential than the other side of a device, and that is given a positive sign. The lower potential side is given a negative sign to it. Positive voltage will require that current go in to the positive terminal. This will be a voltage drop, and we will have to track the algebraic sign of the voltage. The opposite situation is a voltage rise associated with some kind of voltage or current source. And we'll define that as negative voltage. As I have it indicated here, this is a positive voltage in the correct way that current should flow into a positive voltage. The final quantity we're going to need to analyze circuits is electrical power. Power, as you see by the definition, is the time rate of change of energy within the circuit, and must have the units of joules per second. We call joules per second a watt, and we'll use the symbol W for watt. If you expand this definition of the time rate of change of energy, we can find that an equivalent definition of electrical power can be made in terms of voltage and current. And when we say voltage, we're referring to the voltage across the device that is dissipating the power. And we're referring to the current through the device that is dissipating the power. It's a very critical concept. Voltage always has 2 points associated with it. The point of higher potential and the point of lower potential. Whereas current is a single point concept. This summarizes the 3 circuit variables that we've now defined from our basic variables of charge and energy. We have current, which we use the symbol I, and it's measured in amperes. We also have the concept of voltage, where we're using the symbol V to represent voltage. And our unit is volts, with the symbol V. The third circuit variable that we'll need to analyze both AC and DC circuits is power. We use the symbol P for power, and it's measured in watts with the symbol W. You may wonder why we've gone to all the trouble to define another set of variables when we had 2 perfectly good ones to start with. But charge and energy are very difficult to measure with laboratory instruments and to work with mathematically. So it will simplify the analysis greatly by moving to the concepts of current, voltage, and power. Now this diagram here summarizes the relationship between our basic variables we started with, that of energy, charge, and time, and how we've been able to define 3 other circuit variables, the first of which was current, defined as a time rate of change or flow rate of charge within the circuit. The second is that of voltage, and it's defined as the change of energy for a packet of charge as it moves from point A to point B within the circuit. And the final circuit variable was power, and it's defined as the time rate of change of energy. We also found an alternate definition of power in terms of our circuit variables, that being the product of voltage and current. So the circuit variables are shown here outlined in white, and the device variables are shown in red here. They are the variables that we use to define the input-output relationships for the resistors, capacitors, and inductors, the devices that will form circuits. So let's move on to look at a few of these circuit elements that we need to be concerned with in circuit analysis. The first element we'll want to talk about is that of a resistor. We'll use the symbol R for a resistor, and we'll measure the resistance in ohms. This is what we'll term Ohm's law for the resistor, the fact that resistance is equal to the voltage across the resistor divided by the current through the resistor. This is our circuit schematic, our way of representing a resistor in the circuit. It also has a current associated with it and a voltage, and the symbol for the resistor is an R. We use the symbol omega as a shorthand notation for ohms. So now looking at our circuit variables, we can define certain input-output relationships for the resistor. The first of these, if we're given voltage across the resistor and the value of the resistance, we're then able to decide on what the output or current is in this case, the current through the device. Another possibility would be to be given the current through the device and the resistance, and then we're trying to specify the voltage across the device. The second element we want to consider is that of the capacitor, where the resistor is the only element that will dissipate energy. Both the capacitor and the inductor store energy. The capacitor stores energy in its electric field. This is the Ohm's law relationship for a capacitor. We find that current divided by the time rate of change of voltage specifies the capacitance of the device. And capacitance will be measured in farads. Now, this time our circuit schematic looks like this, where we're using the symbol C to represent the capacitor. And the symbol for farads we're using is a large F. Now with the energy storage elements, the inductor and the capacitor, the input-output relationships are a little more complex. Our first input-output relationship in terms of our circuit variables is if we're given the voltage across the device, we can then take the derivative of that voltage, multiply it by the capacitance, and find our output, or current. The inverse relationship, where we're given current through the device, and we're interested in finding what voltage must be across the device, we apply the opposite operation of integration, integrate the current over some time interval, multiply by 1 over the capacitance, and that voltage, represented by the integral, plus whatever initial voltage appeared on the capacitor, will be the voltage across the capacitor, or our output in this case. The third circuit element we wish to look at is another energy storage device, and this time the energy is stored in the magnetic field of the device. This is the inductor. This is the Ohm's law relationship that defines inductance. This time it's the voltage across the device divided by the time rate of change of current through the device. We use the symbol L for inductance, and we'll measure inductance in henries. Our circuit schematic this time, shown here, with the normal polarity convention and its associated direction of current flow. We use the large symbol H for henries. And the thing that we're most concerned about, again, for circuit analysis, are the input-output relationships that apply to this device. Now this time, if we're given voltage across the device, we have the opposite situation from the capacitor. We now must integrate the voltage over some time period from 0 to t, divide by 1 over the inductance, and take this voltage, as represented by the integral, and add to it whatever, that was a current, and add to it whatever initial current was flowing in the inductor. And that will be the current through the inductor at time t. The opposite relationship can be found when we're given the current through the device, taking the derivative or time rate of change of current through the device, multiplying it by the inductance in henries. We'll then obtain our output or voltage across the device. Okay, the final ingredient we need to do circuit analysis are based on the conservation of charge within the circuit. But before we look at circuits, we need to look at a couple of terminology or definitions that will be required to define voltages and currents within the circuit. The first concept is that of a circuit itself. And down below here I have an example of a circuit. It is simply a collection of devices such as resistors, capacitors, inductors, like we were just looking at. And this is one particular circuit. The other concept is that of a node. This example contains 4 nodes. They're simply points between circuit elements. This area in here is one node. This is a second node. And here we see a third. And this whole region through here is the fourth and final node that appears in this circuit. Another fundamental idea is that of a loop within the circuit. This example contains 3 loops. We have one each around the window panes, we'll call them, in the circuit. One traversing here, and one around this way. And we have a third loop that traverses the outside of the circuit. A closely associated idea with loop is a mesh. And a mesh is simply a loop that traverses around the window pane. And mesh is the concept that we'll be most interested in circuit analysis. So now the final concept we need are some circuit constraints that are derived from the basic idea that current can neither be created nor destroyed within a circuit. The first law we'll need to work with and define is Kirchhoff's voltage law. Kirchhoff's voltage law states that the algebraic sum of the voltage around any closed path within a circuit must equal 0. Stated mathematically, it can be represented this way, as the sum of the voltages around any loop is equal to 0. A very important critical concept there is the concept of the algebraic sign associated with a voltage. We saw that devices have polarities associated with them, and we must carefully track the direction of the polarity in order to assure that our sum of voltages will come to 0. If we do not keep track of the algebraic sign, then this law cannot possibly apply. This is an example of Kirchhoff's voltage law. Here we have 5 elements that form a mesh or a loop, and we have an associated polarity for each device. We're going to go around the loop in this clockwise direction, and our algebraic sign associated with each device will be positive when we go from positive to negative, and in the case we're going from negative to positive, we'll call that a negative voltage. This is related to a voltage drop, which we're defining as positive, and this is associated with a voltage rise. We're defining that as negative. So Kirchhoff's voltage law will tell us, looking at this loop, that the sum of the voltages around the loop must equal to 0. V1 then, by our definition, will be positive. We see that V2 must then be negative, going from negative to positive. V3 is again positive because of the polarity of the device. V4 is again positive, and finally V5 is positive. So Kirchhoff's voltage law tells us that this summation of voltages must sum to 0 at every instant in time. Now the second law we need to work with circuits is Kirchhoff's current law. Kirchhoff's current law says that for each node in a circuit, the algebraic sum of the currents going into the node must equal 0. Stated mathematically, you can see that the sum of currents at each node sums to 0. Now again, since current has direction, it's very important to keep track of the fact that we said going into the node is our positive direction. Therefore, currents coming out are negative currents. Here's an example of a node that might appear in a circuit. And we have I1 going into this node, I2 coming out, I4 coming out, and I3 going into the node. So by our definition, I3 and I1 are positive currents, and I2 and I4 are negative currents. So applying Kirchhoff's current law to this node, it tells us that I1 minus I2 plus I3 and minus I4 must equal to 0 at every instant in time. Now we've looked at some basic circuit variables, voltage, current, power. And we've also looked at some devices that, when tied together, will form circuits, that being a resistor, inductor, and capacitor. But we will also need to have some method of generating signals. Signals we'll define as current and voltage themselves. And to do this, we have current and voltage sources. So the next thing I want to look at are the two types of sources that we can define, a voltage source and a current source. Looking at the voltage source, we have two symbols that we use for ideal voltage sources. This first one, shown as a circle with positive and negative signs, is an AC voltage source. It produces a voltage that varies with time. The classic example we'll take a look at is the sinusoid, either a cosine or a sine. We use a separate symbol to represent DC voltage. This is the kind of voltage you would find in a battery. This is simply a series of short and long bars. Now, by our conventions, we would have a current coming out of the positive terminal and going into our circuit in both of these cases. We also have a schematic of a more practical voltage source. It's the same original source plus some internal resistance for the source. Now, it's the characteristic of voltage sources that they will produce a specified voltage. In this case, as you see on the schematic, Vs. This can be 10 volts, 1,000 volts, whatever we decide upon. And then no matter what the circuit elements we put around the source, it will continue to produce that voltage. And the current that comes out of the source then will be determined by the circuit elements themselves. Now, the opposite case that we could define is a device that would produce a constant amount of current, no matter what kind of devices we would put in the circuit around it. And this is our definition of a current source, our second source. This is our symbol for a current source, simply a round symbol with an arrow going the way the current, positive current would flow. This is our ideal current source. Now, the voltage that you would see across the current source is determined by the circuit elements around it. This is a practical current source, where we again have some internal resistance associated with the source itself. And we must take account of this resistance in any circuit analysis problems we look at. Now, the next thing we want to look at is the idea of AC and DC signals. Our signals, as I said before, are going to be the current and voltages within our circuits. DC means that we'll have some constant value, either voltage or current, and we'll usually be limited to looking at only resistors in such a network. That'll be the subject of lesson 2. If we have AC sources or signals, whether they be voltage or current, then they'll change with time in some manner. And I have 3 examples here of the type of signals or waveforms that we'll normally encounter in circuits. The first one is a current listed as -4. This is an example of a DC current. It does not change with time. V of t here, shown as the second example, is the first example of an AC voltage. It's aperiodic, meaning it does not repeat its shape over and over. And it's normally associated with transients in electrical circuits. The third example, however, is the premier AC waveform that we'll be looking at. That is the sinusoid. In this case, it is periodic, and the shape of the voltage repeats itself again and again with some definite period t. And when we're looking at circuits with this kind of a signal or voltage or current source, we'll term that steady state analysis. This is a picture of what a sinusoidal signal looks like. You see, to specify a sinusoidal signal, we must define 3 quantities. The first is its height from the 0 level up to its peak value. It's termed its amplitude. Since the waveform repeats its shape again and again, the other thing that we need to define is the waveform's period. Shown here is t, the time between the same point on its wave shape. And the final definition we need to make is a time shift from the time t equals 0. Shown here as a little a. When we're given those 3 quantities, we can then write any sinusoid based on the wave shape that we see in front of us. For instance, in this case, we'll use a cosine. It has an amplitude A. This is its frequency in radians per second. And this is its phase angle, defined in terms of the time shift from time t equals 0 and the period of the wave. This phase angle is defined in radians. This tells us how much the wave is shifted either left or right. A positive sign associated with the phase angle indicates that we have shifted the waveform to the left, whereas a negative sign associated with this phase angle indicates that the wave has been shifted to the right in time. Shifting to the right corresponds to delaying the signal in time, and shifting to the left causes the signal to occur earlier in time. Closely associated with these ideas are the ideas of frequency, which is 1 over the period of the waveform, and we measure frequency in hertz, or cycles per second. And period itself can be expressed as 1 over the frequency. There's an inverse relationship between the period of the waveform and the frequency of the waveform. Shown here are two relationships that are very useful when we're working with AC circuits. This first relationship allows us to convert a cosine waveform into a sine waveform simply by shifting the cosine wave 90 degrees to the right, or pi over 2 radians. The second relationship we see here allows us to change a sine into a cosine waveform. We do this simply by shifting the sine 90 degrees to the left, forcing it to occur earlier in time. So we see that cosine and sine waves are equivalent to each other and only differ by some phase angle. Two other concepts that are essential in defining the shape and the usefulness of different wave shapes and signals, whether they be voltages or currents, are the concepts of average value and effective value. The average value of a waveform is simply the integral, or the area under the curve of the waveform in one period divided by the period. It's equivalent to an average height over one period. Another characteristic of the waveform we can define is the effective value of the waveform. And this is very useful when we're talking about AC circuits and their effective heating value, how much power they will produce. In this case, our definition is a little more complicated, but again, it represents an average over the period of the waveform. This time, before we average our waveform, we square it and then carry it through the averaging process and take the square root of that value we obtained. This is termed the effective value, or the root mean square of the voltage or current. We've really now defined all the concepts we'll need to do circuit analysis. We have the concept of circuit variables, current, voltage, and power. We've looked at the three devices we'll be interested in: the resistor, the capacitor, and the inductor. And due to the conservation of charge within the circuit, we've been able to arrive at Kirchhoff's voltage law and Kirchhoff's current law, the basic tools that we need to do this circuit analysis. So now I'm going to look at a couple examples to kind of reinforce some of the concepts that we just went over. First example, we have a current, in this case, it has both a DC and an AC component. And this is the mathematical expression for the current. The DC component is represented by the constant current I, and the AC component is represented by the sinusoid with an amplitude of Im and some angular frequency omega. We see that this current flows through a resistor which has a value of R ohms. And we wish to find the average power dissipated per cycle. Now our basic starting point will be Ohm's law. V is equal to IR. In this case, one of our input-output relationships that we developed for the resistor. We'll be given the current going through the device, and we know the resistance, and from there we're able to decide on what must be the voltage across the device. Or in this case, we have a voltage with a DC component, simply a change in magnitude from the current, and a voltage with an AC component. Now, one of our basic electrical variables was that of power. We saw that we could define that in terms of the product of voltage and current. But unfortunately, if we just multiply voltage and current together in this case, we will get what is termed instantaneous power. And the problem is asked us to average that over one cycle of the power. Because voltage and current both have a period, the instantaneous power will also have the same period. So in this case, we need to use the definition of the average value of a signal. In this case, we want to look at the average value of power. So looking at that definition again, our average power is simply the integral of the instantaneous power expressible as a product of voltage and current. And we're getting the area under the curve of power. And we're going to divide that by the period in seconds. Here it's been expanded in terms of voltage and current, the other two circuit variables, which in this case are the two circuit variables that we have been able to arrive at. Substituting in for voltage and current, we can then use the property of integrals that they are linear operators and expand this into the components that you see below. This first component represents the DC termed averaged over one period. That will simply give us back the DC power. Second term is an average of the sinusoidal component that we obtained. When we average a sine wave over one period, its average value will be 0. And that's reflected in this 0 you see below. And the final component of the power dissipated in the resistor involves a sine squared term. This time that will give us a contribution from the AC voltage and current within the device. And when we carry through with the integration, it turns out to be RIm squared over 2. So here we find that the average power dissipated in our resistor with this particular current going through it involves the DC power and the AC power. So I'm going to go through one more example to define some of the relationships, our input-output relationships, rather, for devices. We've seen that given either voltage or current, we have a relationship for defining what the other variable must be. If we look at this second example, it shows a voltage source in this case, producing a voltage of 2T. We have a switch in the circuit that does not allow the voltage source to connect it to our two devices, a capacitor and an inductor. This capacitor has 1 microfarad of capacitance, which is 1 times 10 to the minus 6 farads. The inductor has 1 millihenry of inductance. That's 1 times 10 to the minus 3 henries. Now, as the problem states, the switch will close at time t equals 0. That will then apply our voltage across both the capacitor and the inductor. So our input in this case is voltage, and we wish to decide on the two outputs, I1 and I2, going through the inductor. So we have the input-output relationships to do this. If we look at the first of these, the fact that the current through the capacitor is defined by the capacitance times the time rate of change of voltage. We saw from our circuit schematic the capacitance was 1 times 10 to the minus 6. And now we take our voltage, our 2t, and decide on the time rate of change of that. Taking a derivative, that simply becomes a 2. And we see that the current, I1, going through our capacitor is 2 microamperes. And I've graphed it here. It's simply a constant current. Now, using the other input relationship for the inductor, we can now arrive at, given the same voltage is applied across the inductor, what must be the current I2 going through the inductor. In this case, I've done the calculation down here at the bottom. I2, the current going through the inductor, is simply our 2 millihenries, 1 over the inductance. And I'm sorry, but I guess that should be 10 to the minus third, 1 over 10 to the minus third. And we're going to integrate the voltage across the inductor. Carrying through with the integration and evaluating it from times 0 to time t, we see that the current, in this case, going through the inductor is t squared times 10 to the third. And this is a graph of what we could expect as far as current going through our inductor. So for the two devices, we're given the same voltage across them, and using our input-output relationships for the inductor and the capacitor, we've been able to decide on what the output must be for both devices. In this case, it was current. So we've started from the two fundamental concepts of charge within the circuit and the associated energy for the charge, developed in our circuit variables current, voltage, and power. And using voltage and current, we've been able to arrive at 6 input-output relationships, 2 each for the resistor, capacitor, and the inductor. And then based on the conservation of charge within any circuit, we arrived at Kirchhoff's voltage law, which told us that the algebraic sum of the voltage around any closed loop in the circuit must sum to 0, and Kirchhoff's current law, which tells us that the algebraic sum of currents at any node within the circuit must sum to 0. These will be fundamental from now on in circuit analysis. We then looked at 3 wave shapes. 2 were particularly important. One was the DC, or the constant either voltage or current, and the other was the sinusoid and its various characteristics that will be used in AC steady-state analysis. So we then looked at 2 examples of how to apply these principles to various devices and situations. With that, will conclude today's lesson on fundamentals of electrical engineering.